Hello, everyone. My name is Sohail Khalil Shadiani, and I'm a PhD student at Pennsylvania State University. Today, I'm going to present data convection, GPU-driven case study for thermal-aware data placement in 3D DRAM. First, let's talk about the motivation of this paper. During last decade, due to applications such as deep neural network and graph processing, the memory footprint is increasing rapidly. So we need more on-chip DRAM capacity to accommodate this DRAM requirement to achieve the optimal performance. Current vendors are using a 3D structured DRAMs that, such as HBM and wide I/O, that stacked multiple layers at the top of each other and place them in a 2.5D fashion near the processing unit. In order to increase the capacity of this type of DRAMs, we may either increase the number of layers or increase the size of each layer. Both of them actually increase the package size significantly, which current vendors are not motivated toward it. So it means that we are actually facing a high performance overhead because of the excessive data movement between the host and the disk. So here I will summarize this paper about summarize the motivation, the problem, and how we are actually planning to solve this issue. The motivation of this paper, as mentioned, was that the memory footprint is becoming larger and larger over time. The solution that we are working on is that we can stack 3D DRAM vertically at top of the processing unit in addition to the current 2.5D memory. It can improve the performance, and it is currently actually extensively researched over last decade. So the problem that this approach has is that there is a huge temperature variation in the vertically stacked DRAM because the main heat source of the core is the processing unit. So when the temperature varies from one section of DRAM to another section, it means that the refresh rate is also different in different locations, and it will cause a non-uniform access latency in the DRAM. So how we can use it is that we can actually place the most used data in the sections with the lower access latency. And also at the same time, we want to minimize the number of conflicts by placing two hot segments in the same bank or channel. The mechanism that we use here is that we are sorting the segments based on their rank. And we are allocating the segments to different banks based on the temperature of the GPU and DRAMs, and also based on the number of conflicts. And we are periodically update this allocation. We propose three variation of data convection to achieve better performance, and also at the same time, we don't want to minimize the band, and we don't want to increase the bandwidth consumption significantly. This is the outline of this presentation. First, I will talk about the background in this area, 3D plus 2.5D DRAM integration, what is this one, and why DRAM refresh is important. Then I will talk about the motivation of this paper, why we are facing temperature variation across layers of DRAM, and how can we use it to our benefit. Then I will talk about the prior works and what are the design goals of this paper. Then I will propose three variations of data convection and evaluated using a framework contains Ramulator, GPU theme, and also hotspot. Then I will conclude my work, and then if you have any questions, you feel free to ask me. So, what is 3D plus 2.5D DRAM integration? In a usual DRAM, usually we have only one 2.5D DRAM placed near the GPU. So in this paper, we are actually considering another case, that we have a 3D stacked DRAM at top of the GPU in addition to 2.5D stacked DRAM. It is important because it can increase the capacity by storing more data on chip, and also it reduces the distance between memory and disk. It increases the bandwidth because we can have multiple concurrent access to the memory, and also for 3D DRAM, because of the lower distance and lower number of plugs to access the data, 3D stacked DRAM has lower access time. But there is an issue, temperature issues. As you can see from this picture, the temperature is significantly higher the 3D stacked DRAM, and also there is a temperature variation even within the 3D stacked DRAM. And why it is important? It's because of the refresh rate. DRAM cells contain a transistor and a leaky capacitor. Capacitor leak charge over time, and memory controller periodically refresh capacitors to maintain integrity. So usually the refresh period is 64 milliseconds in the papers, and during that refresh period, data cannot be accessed. So it means that each 64 milliseconds, we need to access the data to make sure that the capacitor is charged fully. The issue arises when the temperature increases. If we have a higher temperature, it causes the capacitor to leak faster. So it will cause the retention time to decrease. It means that, for example, for 70 to 75 degrees centigrade, we need to refresh the DRAM cell each 128 milliseconds. But when the temperature rises to 100 to 105, the refresh rate should be increased to each 16 milliseconds. So it means that different part of the DRAM will face different refresh rates. So now let's see what is the extent of the temperature differences. So in the 3D DRAM, we simulated the temperature of the system using a couple of benchmarks, and we saw that there is a huge temperature difference within layers and across layers. For across layers, we find that there is a temperature differences of up to 20 degrees centigrade, and on average 12.4 degrees centigrade with across layers. And the reason is that GPU is the main heat source, and heat escapes vertically. So different layers face different amount of heat, and because of that, we have a high temperature difference across layers. For within layers, the reason behind it is that different sections of processing unit actually generate different amount of heat. For example, DRAMs, cores, each one of them generate different amount of heat, and based on that, different DRAM actually sections are facing different amount of temperature. So for 2.5D, on the other hand, these temperature variations are minimal because we don't have any GPU at the bottom of the core, and also the heat that is generated by DRAM is significantly lower than the processor power. And another thing about the temperature variation within layer is that the power numbers of DRAM layers are comparable because usually the DRAM are accessed in a uniform fashion. So prior work, in order to address them, they propose two approaches. They either increase the refresh rate for different sections, or they adjust the frequency. For increasing the refresh rate, it means that if the temperature is higher for one section, we only increase the refresh rate. It will cause that the data integrity to be completely correct, but it decreases the performance because we need to, some part of the DRAM need to be stalled more frequently compared to other, and the temperature issues are not addressed. For adjusting the frequency, on the other hand, this approach reduces the frequency for sections with high temperature. It will reduce the temperature for those sections, and it will ensure the integrity of the data. But at the same time, performance is degraded because the frequency of some of the cores are reduced. And this approach actually improves the temperature variation at the cost of the performance. So both of these approaches actually affect the performance of the system. In this paper, we actually aim to optimize data placement. It means that we want to use, actually place the high use data in the sections with low refresh rate. We want to dynamically update the data placement, and we want to reduce the overhead of data migration. At the same time, we don't want to increase the number of conflicts. By conflicts, I mean that, for example, suppose we have two hot data placed in the same bank, and when we want to access them simultaneously, one of them should wait for other one. So it means that we are facing a conflict here. So in this approach, we want to actually place the data according to the temperature, but at the same time, we don't want to increase the number of conflicts significantly. So the overall design of our approach is like this. We start with the initial segment allocation. Segment allocation means how data is initially placed on the DRAM. We sort segments based on the number of accesses and rank them within each segment group. Filter cache is used for sorting and to minimize the sorting overhead. This paper is previously presented how we can actually calculate and sort the number of accesses in the DRAM. So then, based on the rank, we will update the allocation and migration of the segment, migrate the segments. It means that we try to migrate the hottest segment to the coldest layer. Then we will, actually, the only thing is that we don't want to migrate all of the pages because it will cause a huge overhead on the system. So in this approach, we are using a threshold. The results that are presented are using 20% of the top pages, but some other thresholds are also considered as part of the evaluation section. It means that only top 20% of the pages are migrated, and the remaining are using this initial segment allocation. Then we will wait for a period of time, and we will continue this approach. It means that we will iteratively update the mapping to make sure that we are achieving the most optimal data allocation. The first scheme that we propose is that we want to actually place the hottest segment to the coldest bank in each layer. So in order to do that, we created a segment groups that are span across different banks within each layer. So it means that we want to exploit from intra-layer temperature variation, and we know that this is the minimum temperature variation, but it is still significant. So at the same time, we don't want to increase the number of conflicts. So we will increase the bank level parallelism in a way. So to do that, we will distribute the segments across banks in a round robin fashion. So it means that hottest segment will go to the coldest bank in the layer of segment group. Second hottest segment will go to the second coldest bank in the layer. And it will continue in this way until all of the segments are allocated. For interlayers scheme, on the other hand, we are focusing on interlayer temperature variation. It means that the temperature variation across layers. Segment groups span across same bank number in different layers. So it means that hottest segment can be placed on all of the layers, but it should be in the same bank across all these layers. By doing so, we focus on increasing the channel level parallelism, and we want to distribute segments across banks in a round robin fashion to minimize the conflict. So in this way, the hottest segment will go to the coldest bank across layers. Second hottest bank will go to the second coldest bank across layers, and so on and so forth. To actually exploit from both these approaches, we presented a new approach, intra plus interlayer scheme. So in this scheme, each segment can be migrated to any bank in any layer. Okay, we want to exploit from both interlayer and interlayer temperature variation, which is the highest temperature variation that we can see. We want to increase the both channel level and bank level parallelism, and to do so, we will place the hottest segment into the coldest bank across all the layers, second hottest segment into the second coldest bank across all layers, and so on and so forth. For actually our experimental setup, we use GPU as the processing unit, and we modeled it using Mafia, and GTX 480 is actually used for this system. The reason is that the GTX 480 is the only floor plan that we could find as part of the simulation of the system. DRAMs are modeled using Ramulator, and we use 2 dice of HBM version 2 to do this thing. And we employ single bank refresh so that each bank can be actually refreshed individually. Then the power distribution values are calculated using GPU watch. GPU watch is part of the GPU sim that is used for calculating the heat dissipation numbers. And then using the power dissipation values and the floor plan, we calculated the temperature value, and we passed them to GPU sim and Ramulator for updating the allocation. We want to emphasize that GPU is only used for as part of this experiment, and our approach is applicable on all of the processing units, such as CPU, GPU, and other things. The methodology that we use in this work is that the experiments are used in the multi-programming environment. So for simplicity, we use 2 workloads that are executed at the same time. We use 14 workloads with higher footprints, and because we want to use 2 workloads, we actually have 196 different combinations. Some of them actually are not benefiting because, for example, some of them are not even accessing the memory. But in order to make sure that all of the different combinations are valid, we actually experimented all 196 different combinations. Then for the baseline, we use a 3D plus 2.5D DRAMs integration with default data placement, and we also use DVFS to ensure they operate within their TDP. These are the results that we get from our approach. First thing about execution time, we saw that on average, we are achieving about 14.4 average performance improvement, and the improvement is up to 36.4%. There are small cases that we are seeing performance degradation, and this is because, for example, when 2 compute-intensive applications are running at the same time, by migrating and updating the allocation, we are not seeing any performance improvement. But these performance degradations are minimal because of the threshold that we are considering as part of our work. For the energy consumption, we see 9.3 overall energy consumption decrease, and 15.3, actually 24.6 memory access energy consumption decrease. But at the same time, we are increasing 15.3% energy consumption because of the migration overhead. So to conclude our work, in this work, we propose data convection, a novel approach that dynamically migrates data segments to address this temperature variability across DRAMs. We migrate hot data within a layer, across layers, and across both DRAMs. And we balance then both bank level and channel level parallelism. The key results that we have is that we are improving the performance by an average of 14.4% over an optimized baseline, and we are decreasing the memory access energy consumption by 24.6% and total memory energy consumption by 9.3%. Thank you very much, and if you have any question, I'm happy to answer.